All right, in this video, we are going to talk about the difference between molecular formulas and empirical formulas. Okay, one of the things that I think is often important that we don't always do in chemistry is to go back and look at the words that we're using to describe things. We can give a definition of an empirical formula, and we'll do that in just a minute. But I think sometimes it's helpful to go back and look at the definitions so you can understand where these terms come from and how they're related to how we actually deal with things chemically. So the word empirical, if we're talking about empirical formulas, empirical means based on inspection or demonstrated by the data, right? So people talk about empirical evidence, or it's empirically true that this fact, people use that when they're doing political arguments and things like that. So anyway, empirical just means supported by the data, or by looking at something, by inspection. So how does that relate to an empirical formula? Well, we'll see in the next video, not in this one. We'll look at how we can use data in order to determine an empirical formula, right? So the word empirical in this sense means that it comes from the data. You can analyze a compound and use that data to determine the empirical formula. Okay? But what an empirical formula means in simple terms for us is just a formula for a compound Okay, so let's say this empirical formula is just a formula for a compound in which the numbers of atoms for each element are expressed as the simplest possible ratio. Originally I wrote lowest, but I think simplest is probably a better term here. Okay. And this is in contrast to the molecular formula. The molecular formula expresses the actual number of atoms of each element in a compound, and the empirical formula expresses the relative numbers of atoms in a compound in their simplest ratio. So let's take a look at an example that will make that a little bit more clear. All right, so we can compare molecular formulas and empirical formulas for a couple of compounds. Let's take, for example, benzene. And benzene looks like this. There's a bunch of carbons arranged in a hexagon. Right? And there's some alternating double and single bonds here. That's not really important for us right now. But we've got 6 carbons arranged in a hexagon, and each carbon is connected to 2 other carbons and connected to a hydrogen. So this is what the molecule looks like. The molecular formula, we just count up all the carbons and the hydrogens. We see that there are 6 carbons and 6 hydrogens. So this would be our molecular formula. Right? The empirical formula is just the lowest possible set of numbers that expresses this same ratio, right? So because they're the same number of carbons as there are hydrogens, the empirical formula would just be CH, meaning for every carbon there's 1 hydrogen. Okay. Sometimes it turns out that the molecular formula and the empirical formula are the same. So for example, water, which you know is H2O, right, has 1 oxygen atom and 2 hydrogen atoms. So the formula here is H2O, and the simplest possible ratio to express that, our empirical formula, would also be H2O. Right? What we're really looking for, mathematically speaking, is we're talking about the lowest common factors. I think that might be the term that's used in elementary math when we're talking about this process. Or lowest common multiples, maybe that's the term they use. You could also look at methane. So it's like this. And so for the molecular formula, we just count up the number of atoms. There's 1 carbon and 4 hydrogens. And so the empirical formula would also be CH4, because this 4-to-1 ratio is the simplest possible ratio for those. Okay. It's also sometimes true that you can have 2 or even more compounds that have the same molecular formula, or excuse me, that have different molecular formulas, but have the same empirical formula. For example, nitrogen dioxide looks like this. The molecular formula is NO2. The empirical formula is also NO2, but there's also a compound that contains 2 nitrogens and 4 oxygens. It would be dinitrogen tetraoxide. Right? So the molecular formula would be this, and the empirical formula, now if we try to express this ratio of 2 to 4, try to express that in the lowest common terms, or the simplest terms, that would be NO2. Okay. So this is one of the interesting things about molecular formulas and empirical formulas. Anytime you have a molecular formula, you can write the empirical formula, okay? Because all you have to do is find the lowest common factors. Okay? But it's not always the case, let's say, that when you know the empirical formula, you can't always go back to the molecular formula. Because if the empirical formula is NO2, you wouldn't know whether it was this one or this one. Right? So in order to determine between this and this, in order to distinguish between those, we would need some extra bit of information. The extra bit of information that we often use is the molecular weight, right? If we know that the molecular weight, we'll look at these two, obviously the molecular weight of this compound is going to be twice as much as the molecular weight of that compound. So if we know the empirical formula and the molecular weight, we can figure out which one we've got. Okay, here are a couple problems you can use for practice. We'll do these and then we'll do a couple more. Ethylene glycol. I think my handwriting here is sufficient, right? You've got 2 carbons in the middle. 2 carbons are each attached to an OH group at the top and surrounded by 2 other hydrogens below. and then methanol, which is one carbon with three hydrogens around it, and then an OH group on the right. Okay, take a minute, look at those, and write molecular and empirical formulas for each of those. You can pause while you're working on that. All right, so for ethylene glycol, we've got two carbons. Right? We've got, looks like 1, 2, 3, 4, 5, 6 hydrogens and two oxygens. Right? Oops, left off my two oxygens. So for the empirical formula, we just have to find the lowest common multiple of all of these numbers here and then rewrite that in the lowest possible ratio. And it looks like we've got the same number of carbons and oxygens, and we've got 3 times as many hydrogens. So the empirical formula, would be CH3O. Okay. Another way to look at this really is we can take this whole formula here and divide by 2 and see what we get. Right. The key is to change from a molecular formula to an empirical formula. There's got to be some number that you can divide all of these by, so that you still end up with integers on the other side. Okay. So let's look at methanol. Methanol, we've got 1 carbon, 4 hydrogens, and 1 oxygen. So it's CH4O, and there's really nothing we can divide. This, of course, if you don't write anything there, that's assumed to be a 1. Right? There's nothing we can divide all of those by to get lower integers. So the empirical formula for methanol, in this case, is the same as the molecular formula, CH4O. Okay, let's try a couple more. All right, let's look at hydrazine, which has 2 nitrogens in the middle and 4 hydrogens around it, and the ionic compound ammonium nitrate. Go ahead and hit pause and write molecular and empirical formulas for those 2 compounds. All right, hydrazine, you can see there are 2 nitrogens in the middle and 4 hydrogens around the periphery of the molecule. And so N2H4 for the molecular formula, the empirical formula. Again, you can pretty easily see that we've got twice as many hydrogens as nitrogens. So this is NH2. Although if you wanted to, you could also just look at this and say, okay, we're going to take each of these numbers here and divide by 2 and see what we get. All right, ammonium nitrate. We've got nitrogen here, both in the cation and the anion, so there are 2 nitrogens. There are 4 hydrogens. Again, this one looks really similar to the last one, and 2 oxygens. Right, so our empirical formula is NH2O. Okay, let's just throw one more in there because all the ones we've done so far have had really small numbers. So let's look at one that's a slightly larger molecule. Try butane. This is 4 carbons all bound together with hydrogens around the periphery. So go ahead and write the molecular and empirical formulas for butane. All right, you can just simply count the atoms. You'll see we've got 4 carbons and 10 hydrogens. So our molecular formula is C4H10, but both of these are even, so we could divide them by 2. And so our empirical formula would be C2H5. Okay, so this is a pretty short video. Basically, we're just talking about the definition of empirical formula, which is the molecular formula for a compound expressed in the simplest possible ratio of atoms. And we showed that if you know the molecular formula, you can write the empirical formula. But it's not necessarily true that if you know the empirical formula, you can't always write the molecular formula, because from any molecular formula, there may be multiple possible molecular formulas. And we'll look at that in the next video. And then we did a little bit of practice. Okay, so work on those. There are some of those in your study guide. If you think you've got this down, because it's pretty simple, go ahead and jump on to the next video where we'll look at how to determine empirical formulas from data.